Hello and welcome to Tribe Topper. In this video session, you are going to learn about displacement, velocity and acceleration of simple harmonic motion. So first of all, let's talk about displacement. Let's say this is a pendulum, a simple pendulum, and I would rather mark this position as O. So O is the equilibrium position. You pushed it. Suppose you pushed it towards left and it reached the extreme position A. So that means at t is equal to 0, your displacement was 0, right? I'm taking the case where you start the oscillation right from the equilibrium position. I can write that for you. So when oscillation begins at equilibrium position, then we would say at t is equal to 0, your x is equal to 0. Now, after 1/4 of the total time period, because see, it takes 4 parts from 0 to t by 4, 1/4 of the time period you reach position A, then it falls back. So at half time period you reach position O back, then 3t by 4 in the next 1/4 you reach the position C, and at full t you have reached the position back at O, and one oscillation is completed. So at t is equal to 0, x is equal to 0. Then at t is equal to t by 4, your x is equal to x naught. That's the maximum displacement. Then at t is equal to t by 2, you again reach back at the position 0. Then at t is equal to 3t by 4, you will reach back at the position x is equal to x naught again, because at 3t by 4 you are on the other extreme. And then lastly, t is equal to capital T, that's one full time period done, and you are back to the original position, which is mean position. So if you plot these points, the ones that I have just got at t is equal to 0, so along the x-axis I have t, and on the y-axis I have x. Now this x, how does it vary? At 0, my point says 0. At t by 4, my x is x naught. So here I refer to 1/4 of the time period, I reach the maximum point. This is t by 4. Then at t half, I reach 0. Then at 3t by 4, I reach the other extreme. And at full t, I reach back. So one oscillation completed. When you plot it graphically, you understand you get a sine wave. You've learned about sine wave in trigonometry. So this here we would say it's a sine wave which represents the motion of your simple harmonic motion here. So what will be the displacement? Therefore, based on this explanation or the waveform that we are getting, we would say the instantaneous displacement at any point would be given as x is equal to x naught sine of omega t. So x varies with x naught sine of omega t. Omega t represents the theta here. So we can just quickly talk about omega as well. So basically omega represents the angular frequency or angular velocity. So that is represented as angular displacement over time. Omega is equal to theta by t. So theta can be replaced as omega t. Therefore the equation that we got as x is equal to x naught sine theta is rather written as x is equal to x naught sine of omega t. Why we convert this? So that we can write our answer in terms of t, because at various values of t, that means at various instants, accordingly the t keeps changing. When the t changes, x also changes. Right? So this is the equation for the displacement that you can find out for a simple harmonic motion that begins from the equilibrium position. Now let's talk about velocity. Now the same motion we'll study again. Since from the equilibrium position O, we pushed it towards A, that means we pushed it with a maximum velocity. Only then it would continue to move. And while going to the position A, because the restoring force is pulling it back, the velocity goes on decreasing. So that means at t is equal to 0, you had a maximum velocity, say v naught, which is the maximum velocity. But when you reach at t equal to t by 4, when you reach at the extreme position A, obviously the velocity reduces to 0. That's why it falls back. So V is equal to 0. Then it falls back, and obviously restoring force is pulling it back. The velocity goes on increasing, and then at the mean position, again, that's your half time period covered, your velocity reduces, again reaches maximum. Then it continues to the other side. Because of that maximum velocity, the motion continues to the C extreme position. So therefore at 3t/4, your velocity becomes 0 again, and eventually when it becomes 0 again, it falls back, and at t is equal to t, you have again the velocity as maximum. So if you're going to plot this on the graph, that is velocity on the y-axis versus t on the x-axis, we would find that at t is equal to 0, you have a maximum velocity. At t/4, you reach a 0 velocity at the extreme position. Then at half time interval, you reach back at the equilibrium position. You have a maximum velocity in the opposite direction now. Then it reaches back. This is this is t/2, this is 3t/4, and finally at t it reaches back again to the maximum position. So this is how you will plot the points, and eventually you will get this curve. Now what curve is this? This is obviously a cosine curve. So therefore we would say the velocity would be represented as the V naught times cos of omega t, because at various values of t, like when you put t is equal to 0, you obviously get V is equal to V naught times cos of 0, and that is cos 0 is 1, so V is equal to V naught, which is our maximum. When you do t as t/4, so your omega accordingly changes and it becomes cos 90, and so you will have the 0 velocity. So if displacement is x is equal to x naught cos sine omega t, the velocity is given as v is equal to v naught cos omega t. And the last thing we have is acceleration. Now if you look at it carefully, at t is equal to 0, that is when your motion started, your acceleration was 0 because there is no force acting right now. But once this object reaches this A position, the restoring force tries to pull it back. So at t/4, that means at the position A, there will be a maximum restoring force acting at the extreme position, and so you will also have the maximum acceleration A naught. Then at t is equal to t/2, you come back again at point B, no force acting, equilibrium position, acceleration again drops to 0. Then you go to the other extreme, that's 3t/4. At the position C, again the force, the restoring force is maximum because this is the farthest point, so acceleration would again be maximum. So your acceleration, how does it varies? But you have to understand one thing, that the acceleration, we talked about it in a simple harmonic motion, is proportional to negative of x. This would just indicate that when x is positive, right, when x is positive and maximum, then your acceleration A is negative and maximum. So if we say our x is positive, we would say this starts with 0, then at the maximum position or on the top position of x, your corresponding position of acceleration would be negative max. Then it comes back to 0 at the mean position, and then in the opposite extreme position, when x is negative, your acceleration reaches the positive, and then it drops to 0 again. So you have a sine wave again, but this is a negative sine wave. Since this is a reflected sine wave, so negative sine wave would indicate that your acceleration equation for any instant would be A is equal to A naught sine omega t. So the three important equations that you have learned in this video session are: one is x is equal to x naught sine omega t when the oscillation starts from the equilibrium position. Then velocity is given as v naught cos of omega t, and acceleration is given as minus a naught sine of omega t. I'll correct it here also. It has to be a negative sign. So these are the three equations. We don't need to derive all of them again, but just to let you know that if the oscillation begins at extreme position, right? If your oscillation started from the extreme positions, the graphs would interchange a bit. So in that case, your x would be starting already from the maximum position. So the graph would indicate that x is x naught cos of omega t. And then velocity would be negative v naught sine of omega t, and acceleration would be back to negative a naught cos of omega t. So there is just a slight change here, that sine becomes cos and the cos terms become sine, because when you start from the extreme positions, you have different instants referring to different displacement. So at t is equal to 0, already you are at x is equal to x naught. At the extreme position, velocity has to be 0 and the acceleration has to be a maximum. So accordingly, we get the cosine and the sine waves. That's all for this video session. In the next video session, we are going to talk about some problems based on simple harmonic motion. Thank you.